We're live.
Hello, everybody. Welcome to the third day of QMAT 2021. This is the parallel session 2 in the morning. Before I hand over the session to the session chair, Professor Arnob, a couple of things to announce. One is that the long talks will be 25 minutes plus 5 minutes of Q&A. The questions should be kept for the end of the talk and not interrupt the talk in between. If you have a very persistent question, type it in the chat and we can take it up at the end of the talk. We also have a very tight schedule. So what we would like to do is, if there's an argument that is not getting resolved immediately, there are a few breakout rooms. So, parties can go into the breakout rooms to settle.
Wait, did Rajdeep just freeze?
I think yes.
Yeah, I couldn't hear him.
I think the Rajdeep's connection has dropped. So I think maybe we can.
He's back, I think.
He's back?
Yeah.
Okay.
Hey, was I not audible half of the things?
No, you
The last couple of
breakout rooms.
Okay, so the basic idea is that we have some breakout rooms, and if some questions do not get resolved and people want to continue discussing, you can go to the breakout rooms where the rest of the talk can continue here. And with this, I would just hand it over to Arnob. Arnob, the session is yours.
Yeah, okay, thanks Rajdeep. So welcome everyone to day 3 of QMAT. So in this session, we have 5 talks, 3 of which are invited and 2 are contributed short talks. So the first talk is going to be by Debanjan Chowdhury from Cornell, and he'll be talking about continuous Wigner-Mott transitions in Moiré heterostructures. So Debanjan, I'll give you a warning at around 22 minutes, because, so that you have 3 minutes left after that. Yeah?
Yeah.
Okay,
thank you.
Thanks. Yeah, so please go ahead.
All right. Thanks for that introduction. And let me actually begin by thanking the organizers for inviting me to this exciting workshop and for putting together such an interesting program. Unfortunately, because of the inconvenient time difference, I can't attend most of the talks. Anyway, so yeah, I'm going to tell you about some really exciting new developments in a field that's, of course, been an old and difficult subject in condensed matter physics. And given that it's a short talk, I may not be able to go into all the technical details. The very least that I want to do is convey to you what are the big picture excitements that are currently driving the field. So let me just quickly thank my collaborators. So the young people who have done a lot of the work are Sunghun and Seth, who are grad students at Cornell and MIT, and Liu Jun, who's a postdoc at Perimeter. And much of this work has been done in collaboration with my experimental colleagues at Cornell, Kinfei Mak and Ji Shan, and my long-term collaborator, Sanyal, also from MIT. Okay, so just to give you a punchline right at the beginning, as many of you know, one of the really cool things that's happened in the field in the past couple of years is this discovery of this new platform of Moiré materials in 2D, which really give you an amazing degree of control and tunability to study strongly correlated physics. And specifically, what I want to focus on today is this recent excitement that has been able to realize various continuous quantum phase transitions between metals and Mott insulators as a function of some external tuning parameters. And this is really interesting kind of quantum criticality that sheds really a lot of new interesting light on this very old subject, but from a very fresh and new perspective. So you will actually hear a lot more about this from Abhay tomorrow in his talk, also at the same time, I believe. So I won't really go into the details of this work. Instead, I will give you a very brief summary of what this experiment really sees, and then talk about theory. Okay, so of course, in solid state 101, we always hear how metals and insulators at 0 temperature are really, fundamentally distinct phases of matter with very different properties. And so the question is, if you imagine trying to tune a continuous quantum phase transition between these two different phases, how would that transition look like theoretically? Okay. And for the purpose of this talk, I'm again going to emphasize this. I'm interested in continuous transitions, not first order phase transitions. And moreover, I'm interested in transitions that occur at a fixed electronic density. Okay. So now there are certain basic requirements that have to be met in order to drive this transition. So suppose if you approach this transition from the insulating side, which has an electrical charge gap, what I demand is that this charge gap vanishes continuously as I approach the critical point. Okay. And on the metallic side, if you're at a fixed electronic density, Ladinger's theorem tells you what the total area of the Fermi surface is going to look like. Okay, so if the density is fixed, the total area can't change. But of course, if you're driving this metallic phase into an insulator, the electronic Fermi surface obviously has to disappear. And in fact, it has to disappear abruptly as you cross from the metallic side into the insulator. So the question is, how does that actually happen across a continuous transition? It almost sounds like an oxymoron. If something has to disappear abruptly, how is this consistent with a continuous transition? So before I go into the details of this, I just want to quickly remind you of a few simple and familiar examples of metal insulator transitions. So one example is, that you can already visualize within band theory is that imagine you start out with a bunch of bands where the Fermi energy starts out by being in the gap between two bands. So you have an insulator here. Of course, if you tune the Fermi energy or the chemical potential, at some point when it intersects the band, you get a Fermi surface. Okay, and so, but what's happening here is that the size of the Fermi surface is not fixed. Okay, so as you go from the metal to the insulator, it shrinks continuously to 0 and then disappears. So this is also an example of what is known as the Lifshitz transition. Importantly, the Fermi surface shrinks as you go through the transition. The other example of a metal insulator transition occurs as a strength of increasing disorder. So imagine that you start out with weak disorder where you have some kind of a diffusive metal. And then if you crank up the strength of disorder, at some point you really Anderson localize all your itinerant states and you go into an Anderson insulator. And there's a long history, a very interesting and rich history, especially in the 90s, of studying density-tuned metal insulator transitions in various TUDEGs. This is a nice review that summarizes all of this amazing, discoveries and puzzles. But importantly, these are all density-tuned transitions. And here, of course, there are interplay of interaction, disorder, and some of the ingredients that I talked about. Their interplay is what gives rise to all of this richness. But again, this is not what I want to talk about. Instead, I want to talk about a different experiment or a different setup where you have a fixed density. So let's just say for now that we're restricted to a filling of 1 electron per unit cell. So at weak interactions, you have just a Fermi liquid metal with an area of the Fermi surface set by just the 1 electron per unit cell. Now, of course, when the interactions are really strong compared to the bandwidth, you can basically start out by doing perturbation theory in the hopping or the bandwidth. And this is the regime where you have super exchange and well-developed moments. And this is what your Mott insulator might look like. Okay. And so the question is, as a function of W over U, how do you go between these two extreme limits? Okay. Now, moreover, there's an interesting question of whether this Mott insulator necessarily has to break any symmetry spontaneously. So here it has this famous 120-degree ordering on the triangular lattice, for instance. But does it always need to order? Or can it form some kind of a symmetric state that does not break any symmetries? And moreover, ultimately, the main question that we're interested in is, what is the critical theory for the transition between the metal and this Mott insulator? Okay, so this brings me to the recent experiments. I'll just summarize all the key features in 2 slides. So this is what the transport data looks like. So red is very high resistance and blue is low resistance. And the amazing thing about these systems is that, so this is a bilayer of 2 different materials which have a slight lattice mismatch, which gives you this Moiré pattern with a long length scale that's roughly of the order of 5 nanometers or so. So again, this realizes basically a triangular lattice Hubbard model with some further neighbor interactions. And interestingly, what you can do in this system is you can tune the density of electrons in your sample independently of the strength of the bandwidth interactions, okay? So the really interesting stuff is happening in this corner of this diagram, whereby just tuning the electric field that you apply in this direction across the two layers, you can basically change the ratio of bandwidth to interaction. Now, this is of course very hard to do in any solid state material, but that's the amazing tunability associated with these systems. And so you can immediately see that you go from a very resistive state, which is an insulator, to something that's like a metal. And in fact, if you look at the transport data and do the usual kind of scaling collapse, this is what it looks like. So all of these curves, these correspond to the insulator, and all of these curves, they are the metal, okay? Moreover, just by fitting an activated form to the resistance here on the insulating side, you can extract a charge gap, and indeed it vanishes continuously across the critical point. I should have also said that there is no sign of hysteresis in this system. So it really does look like a continuous transition. You can also measure the compressibility that also vanishes continuously as you approach the transition from the metallic side, okay? Now this is all good, but one of the most interesting things about the system is that you can measure the spin susceptibility across this transition. And what you find is that basically as you go through the transition from your Fermi liquid metal to the Mott insulator, the spin susceptibility evolves rather smoothly. Now, this is kind of bizarre if you think about it, because at low temperature in the Fermi liquid, the spin susceptibility really comes from the electronic Fermi surface. So all of these low energy excitations near the Fermi surface contribute to an almost temperature independent susceptibility. But when it evolves smoothly into the Mott insulator, what that basically tells you is that the spin excitations in the Mott insulator, they're not gapped. In fact, it sounds like there are a lot of low energy spinful excitations in the insulator, even though you have a well-developed charge gap. Okay, so this is of course interesting, and maybe the experts already know which way I'm going with this as I proceed with the rest of the talk. Okay, so our goal is then to describe phase transitions in metals that are associated with a sudden disappearance of a Fermi surface, but where there is no onset of any magnetic order. And this is known because in the measurements, when you measure the susceptibility, they've measured it down to 5% of the Curie-White scale, and there is no sign of any magnetic ordering. Instead, you see this lots of gapless excitations that are clearly still carrying the spin quantum number. Okay, and importantly, such a transition is not described by sort of a Landau Fermi liquid coupled to a Landau order parameter. And instead, I'll try to argue that these are described in terms of some other, strongly coupled emergent gauge theories that are coupled to matter fields. And this will also take me to, this new class of deconfined quantum critical points in metals. Okay, so the standard language to describe this kind of a transition requires the so-called partons, where you start out with your electronic operator, which carries both the electrical charge and the spin, and you rewrite it in terms of new degrees of freedom. So the B here is a boson that carries the real physical charge, and the F is a spinon, which carries the fermionic statistics and the spin quantum number, okay? Now you can always write your electron in terms of these operators, but what you've done is introduce extra degrees of freedom, and you have to really project it back to the physical Hilbert space. And what that really means is that there is an emergent gauge field. Okay, so the cartoon picture is like this. There is an emergent gauge field that really is coupled to both the spin-on and this charge-on. And that basically encodes the non-locality associated with these partonic degrees of freedom, okay? So now why is this useful? Well, because once you have introduced these degrees of freedom, let's say we just carried out some kind of a mean field theory for the transition, you have this boson at some fixed density, and you're changing the ratio of bandwidth to interactions. So when the interactions are weak, the bosons will just condense into a superfluid. But the bosonic superfluid actually just corresponds to the Fermi liquid phase. The way to see that is when the boson condenses, this is just a C number. So you have basically just renormalized your electron. Okay. But then at the same commensurate density, when you crank up the strength of interactions and W over U is small, that's where the boson goes into a Mott insulating phase. Okay. And develops a gap. This is the charge gap in the system. Now, if these spin-ons, they continue to have a Fermi surface, And what you have essentially realized is an electrical insulator because of the charge gap coming from these bosons, which coexists with a Fermi surface of these spin-ons. Okay. And as it turns out, the experiment that has been done recently that is remarkably consistent with a lot of the ingredients associated with this transition. And I'm going to describe that in a second. So this is sort of the mean field picture, but one has to really go and analyze this complicated field theory to really describe what's going on. And so one can just write down the low energy field theory that would capture this transition, which is basically what I'm doing here. So the bosons are described by some kind of a relativistic field theory here. But importantly, this is not your standard superfluid to Mott insulator transition for the bosons because the bosons carry a gauge charge. So this little a that you see, that's the emergent gauge field, okay, which the boson carries a charge under. But importantly, you also have a finite density of these spin-ons, which are also coupled to the same gauge field. Okay, so you have a theory for the spin-on Fermi surface coupled to a gauge field. Now, this is not just it. In fact, your theory should allow for all gauge invariant couplings between your two matter sectors. Okay, so I've just written one of the simplest terms here, but there are in principle all other terms of this type. Okay, so this theory has been analyzed in the past, and it turns out, there are lots of moving parts, but ultimately it can be described, and there is a continuous transition. And what's really amazing is that near the critical point, the sort of the charge on sector decouples in a very dynamical sense from the sector associated with the spin-ons coupled to the gauge field. Okay, so ultimately, this metal insulator transition is basically described by some kind of a 3dxy-like transition for the bosons, which is dynamically decoupled from the Fermi surface coupled to a gauge field. And so the picture is as follows. You start out with an electronic Fermi surface described by a Landau Fermi liquid theory on one side, and then the charge, the boson sort of goes into a Mott insulator, and what you're left with is a spin-on Fermi surface. Okay, and there are lots of experimental predictions that you can make. So I'll just highlight a few. So across this transition, what's really going on is that the quasi-particle residue, which measures the overlap between your electron and the low energy Landau quasi-particle near the Fermi surface, that actually vanishes continuously. And so the electronic Fermi surface sort of evolves smoothly into the spin-on Fermi surface. And across the transition, the boson gap, that is what from the insulating side vanishes. And moreover, you can calculate what the effective mass, the electronic effective mass does, and that also becomes heavier and heavier until it diverges as it should, because of course, as you go into the insulator, you should not have any electronic quasi-particle near the Fermi surface. But importantly, the spin susceptibility evolves smoothly across this transition because the spin sector doesn't really see much of a difference. So it's quite striking that the experiment actually sees many of these features, and there is qualitative agreement, and in some cases, even quantitative agreement. Okay, let me skip this bit for now. So now this brings me to the other question. I mean, why stop at just half filling of the unit cell? Especially given that a series of experiments in just the last 2 years has actually seen a whole panoply of Wigner crystals. Now here, the Wigner crystals, of course, arise due to longer range interactions, but because there is an underlying lattice, they only sort of lock into various commensurate densities associated with the lattice. So, this plot here is meant to show all of the different commensurate Wigner crystals that have been reported till date with their ordering scale as a function of temperature. And interestingly, some of these have even been imaged quite recently, just a few months back. Okay, so now we can ask the question, suppose we are at a different commensurate density. Let's just say maybe we are at 1/3 filling, okay, where experiments have seen some kind of a Wigner crystalline state like that, okay, where every third side is occupied by electrons. If you were to do the same experiment by changing the ratio of bandwidth to interactions, can you drive a continuous transition from a metal which preserves all of the crystalline symmetries to this Wigner crystal? Okay. Now, of course, this is slightly more complicated than the scenario I just described, because in addition to all of the requirements I had specified earlier, there is an additional new ingredient here, which is that this density wave order also has to vanish as I approach the critical point from the insulating side. And of course, you want all of this to happen without any fine tuning. So the question is, can you generically write down a theory for a continuous transition between these two where all of these requirements are met in a very natural setting. Okay. Now, before I describe that, the simplest scenario that you might have imagined is actually the following. So you start out with a completely symmetry preserving Landau Fermi liquid with an electronic Fermi surface. You imagine that there is some order parameter, associated with the translational symmetry that onsets in this metallic state. It reconstructs and actually, let's say doubles the unit cell. And then you just crank up the strength of this order parameter until you drive some kind of Lifshitz transition, okay, to the Wigner crystal, which does not have any electronic Fermi surface. So importantly, in this scenario, there is this intermediate metallic state, which has a reconstructed Fermi surface. But so this is what one would, imagine in the simplest possible scenario, but this is not what we're after. We're asking theoretically, is it possible, at least as a matter of principle, to have a direct transition between this phase and this phase, okay? And to give you the punchline, the answer is yes. Okay, so the story is as follows. So you can go from an electronic metallic state with a well-defined Fermi surface to a Wigner crystal, okay, where you have some kind of translational symmetry breaking and charge order with some coexisting spin-on Fermi surface, okay? So now in this partonic language that I had introduced earlier, what you're really doing is that the electronic sort of metallic state is still the same. So you have some kind of a superfluid state associated with the charge-ons. But now, because you also want to go into a state that has some translational symmetry breaking, what you really need to do is go into some kind of a density wave, a charge density wave associated with these charge-ons, okay? And so immediately you see that there are two different symmetries that are unrelated to each other on either side of this transition. So unlike the previous example where you were imagining driving some kind of a superfluid to Mott insulator transition for the bosons, what you're doing here is driving a transition between a superfluid to a CDW, which is really an example of a deconfined phase transition, okay? So we can go ahead and try to write down a theory for this, and turns out it's more convenient to do that in not the language of these charge-ons, but in a dual picture, okay, where you rewrite the theory not in terms of the boson, but in terms of the vortices. So in 2D, you can describe the superfluid to Mott insulator transition in terms of the vortices instead of the bosons. And the key thing to remember is that anytime you move the vortex around the boson, you pick up a non-trivial sort of periphase, which depends on how many bosons the vortex encircles. And so in this picture, the boson condensate, which is the superfluid, is described by a vortex insulator, and the boson insulator is described in terms of a vortex condensate. Okay, so I see that I'm sort of running out of time, so let me just get to the sort of the key aspects of the theory. So in terms of these vortex degrees of freedom, forgetting about the spin-on for just a little while, you can write down a theory that is consistent with all of the underlying microscopic symmetries of the lattice. The important thing to remember is that these vortex degrees of freedom, they transform projectively under the various lattice translational operations. So one can do that. And in fact, this has been done in the past in a purely sort of magnetic setting, both for the triangular lattice and on the square lattice by people, including some of whom are present in the audience. And basically by just playing around with the bosonic part of the action, you can get all kinds of different charge density wave patterns. I've just drawn a few here. So you have this theory describing the bosons, and the spin-on part is still described by a similar theory like what I had earlier, which is a spin-on Fermi surface coupled to the gauge field. Of course, the interesting thing now to ask again is, once you turn on all gauge invariant couplings between the bosons and the fermions, does it flow to some strong coupling, or do these matter fields decouple again? If they do decouple, then you have some hope of describing this transition purely as some kind of a vortex condensation transition. Now, this is actually much more complicated than the usual 3D-XY transition, but in this recent paper, we have shown that there exists a theoretical limit where all the gauge invariant couplings between these bosons and the fermions are actually irrelevant. So indeed, the transition is just described by some kind of a vortex condensation. And then interestingly, the universal properties that you calculate near this Wigner-Mott transition, they're very similar to the transition that I described earlier at the filling of 1 electron per unit cell. And so the basic picture Looks like this. You
Debanjan,
go from yeah.
You have about 3 minutes left, and then 5 minutes of Q&A. Yeah.
Okay, great. Right. So you basically have, this is the picture that summarizes the transition where you go from the Fermi liquid to some kind of a charge on insulator. And I have chosen a specific ordering pattern here that coexists with the spin-on Fermi surface. Now, because the spin-ons feel the potential due to this charge on order, the spin-on actually gets reconstructed as shown here. Okay. So far in the last few minutes, let me actually switch gears and talk about something slightly different. So in both examples of these continuous metal insulator transitions, at least within this Partonic language, what you see is that the insulating side always has this remnant Fermi surface of spin-ons. Okay, these are of course experimentally hard to detect and probe directly because you can't couple to spin-ons directly, but nevertheless they are there. And so in principle, they should show up in things like thermodynamics and thermal transport. And again, from a theoretical point of view, it's interesting to ask if there are transitions across which you have no Fermi surface whatsoever of even these spin-ons. Okay, and so basically, what you want to describe is perhaps a continuous metal insulator transition where you go from this to this, which is really a fully gapped insulator. So how would you even approach this problem? And one idea of trying to do that within the same setup is to imagine the following scenario. So suppose your basic transition is of this type, where you go into a spin-on Fermi surface state. But what if the spin-ons, and specifically the Fermi surface, likes to pair up because of some essentially PCS-like pairing of these spin-ons? If so, then that would gap out the spin-ons completely. Okay, and in particular, we are interested in the question of whether this pairing of the spin-ons, if that can be, something like a dangerously irrelevant relation. If so, then we can easily describe a continuous transition from a Fermi liquid metal to an insulator that has no remnant Fermi surfaces of anything. Now, it turns out that's very hard to do for the kinds of theories that I've been writing so far. So if you just take your spin-on Fermi surface coupled to the gauge field, it's very easy to understand why the pairing here, why you can't have a spontaneous pairing of these spin-ons. It's basically undergrad level electrodynamics. So this gauge field actually couples to the current associated with the spin-ons. So if you want to turn on a BCS gap, antiportal points on the Fermi surface have to pair up, but these have opposite currents. So if you imagine two opposite current carrying wires, they actually repel each other. They don't attract. And this is why this sort of Amperian, this is Ampere's law. So this Amperian interaction cannot lead to gapping out of the Fermi surface. So what we did recently is, we explored the following situation. So the Fermi surface coupled to a U1 gauge field is sort of the simplest kind of theory that you can write down, or the simplest ansatz you can imagine. Now, it's possible that energetically there are more complicated, gauge groups that show up for this transition. So for instance, you might have a situation that has two different U1s, or something like a U2, which you can roughly think of as a U1 times an SU2. Now, if so, and if these two different gauge groups, have a different tendency as far as the fermions are concerned, meaning, so we know actually from QCD, the color superconductivity in QCD, that SU2 gauge fields actually mediate attractive interaction. Then depending on, which of these two gauge fields has a stronger tendency, you can either get these spin-ons to pair up, in which case you won't have any Fermi surface left, or you won't, in which case you will have a Fermi surface left. Okay, and this is the kind of exercise we have recently done, which I suppose I can't really go into the details of, but I'm happy to discuss this in a breakout room or at the end of the talk. But this is basically one way in which you can have a transition from a Fermi liquid metal to some kind of an insulator that has no remnant Fermi surfaces whatsoever. Okay, so let me actually then end with an outlook. So I guess the most interesting thing is that finally we have an experimental platform where we can study continuous metal insulator transitions, interestingly, to insulators that are basically that look like on spin liquids with potentially spin-on Fermi surfaces. And given that these systems are highly tunable, it's possible that we have many different axes that we can probe and tweak to really study spin liquids. And this is an old article from many years ago, which was lamenting on how there have been very few examples of quantum spin liquids. And okay, back then we thought we had come across a few, but I think now we really have examples where I think we're almost there. And thinking about these kinds of experiments has led us to develop some new conceptual frameworks for describing such continuous metal insulator transitions. And I've only sort of scratched the very tip of the iceberg here. There are lots of interesting questions related to what happens at finite temperatures. You will probably hear about some interesting Planckian transport near these transitions in IISC talk tomorrow, which is of course also relevant for a lot of other strongly correlated compounds. And we need lots of new theory and experimental ideas to directly probe the presence of such fractionalization, meaning how you actually go and look for these non-local quasi-particles. And of course, numerics is something that one has to do to really figure out the energetics of these microscopic models and what's going on. Okay, so I think I'll end there. I might have just gone a little over time, but I'm happy to take questions now.
Yeah, thanks, Debanjan. So maybe we have time for one quick question from the audience. So Krishnendu, please go ahead.
Yeah, Debanjan, one very quick question. So in the context of this transition of bosons, this deconfined transition, where the translational symmetry is broken on the Mott side. Yeah. So subsequent Monte Carlo things in a situation where no fermions were involved showed that it becomes first order. Right. So is there a way that this Pinon somehow saves the day here, or is it known?
Yeah, that's a great question. I don't think especially for the theory that we are writing down, I don't think actually it's known whether that transition is second order or first order. I mean, the IR properties of that theory are just not known. So in fact, to say meaningful things for our story, we have to do some large N type thing. Sure. But yeah, at the same time, it is in fact possible that for that theory, once you add the coupling to the fermions, in fact, at that point, we lose control and we can't even say if this decoupling works. So it's possible that it flows to some strong coupling point, and whether that's first order, second order, is basically unknown. So
yeah, I understand. Sure.
Yeah, that's a great question.
All right. Thanks, Debanjan. Yeah. So maybe if there are other questions, you can take them in the breakout room. So yeah.
Sure.
Yeah. So I think I should now invite Sumilan to.
Hello.
Hi, Sumilan. Can you just share your screen? Yeah, thanks.
Yeah,
so I'm assuming if there are questions and people want to discuss in breakout room, there will be like a chat or something, and then I go there.
Yes, they could private message you on Zoom itself, and you can coordinate with them.
Sure. Okay.
All right. So the next talk is by Sumilan Banerjee from IISC, and he'll talk about quantum to classical crossover in many-body chaos and scrambling from relaxation in spin classes. So Sumilan, I'll give you a warning at 22 minutes so that you have 3 minutes to conclude after that. Okay?
Sure. Yeah.
Okay. Yeah.
Okay, thanks. Okay, thanks, Arnob. Yeah, I'd of course like to thank the organizers for inviting me to give this talk. Hopefully, we'll have a physical meeting next year. Okay, so I'll be talking about something which is somewhat different from what Debanjan talked about, and it's it's not truly quantum condensed matter. I think it's related to also glasses in classical systems, but trying to connect some quantum aspects and using quantum mechanics to tell something about glasses in some sense. Okay, so let me start by acknowledging the people who have done all the works. So these are students, Surojit in physics department, and Lokesh, who is from high energy physics in IISC. And if you are interested, you can find the details of this work in this archive posting. Okay, so let me just start for a very simple thing, just to make sure that we are on the same page. So I'll be talking about chaos, and this is of course a very popular and familiar concept, and generally typically characterized in this way, that you have classical systems, classical trajectories, and what you look at is that compare two trajectories which, let's say, started from very small initial conditions which are only deviated by a small amount at initial time, and then they go apart, and you basically measure this deviation as a function of time, and it is characterized by this Lyapunov exponent. So this is going to be the main thing that I'll be discussing. Only this characteristic of chaos. There are many other characteristics of chaos which I'll not discuss in this talk. And the idea is that this exponential growth that happens over a regime, which in classical system you can make arbitrarily large by choosing this initial deviation in principle. And then for chaotic system you will find some non-zero Lyapunov exponents. For example, this chaotic billiard, these are all single particle chaos. Now, so we'll be of course talking about quantum chaos, and especially for many body systems. So how do you go about defining it, at least in this language? Again, there are many definitions of chaos in quantum systems. I'll only use a very specific particular definition which is related to this Lyapunov exponent. So the idea is actually works for semi-class systems, quantum systems which are close to their classical limit or in the semi-classical regime. And the idea is just to generalize this this definition of Lyapunov exponent, which is in terms of this trajectory divergence or the sensitivity to the initial condition of a trajectory, which can be written as a Poisson bracket using the initial position and momentum. And then what you do is the standard thing that you convert Poisson bracket to a commutator, and of course there is a dimension, so the h bar comes. And this is the way that Larkin and Ovchinnikov first used to actually, who found this kind of objects appearing in theories of superconductivity. And this defines ultimately in quantum mechanics, of course, this object you have to calculate some expectation values, and turns out that what you have to do, you have to take a square of this and then take the average, and that will give you this thing also growing as exponentially as in the classical counterpart. Of course, if you are close to the quantum limit, classical limit, which is measured by this h bar which is in front. So this will become small when h bar is small. Okay. So now for many body system, the idea is to just generalize it and try to see what happens. I mean, basically what you do is you take let's say any two many body operators, let's say some creation or annihilation operator for bosons or fermions, and you essentially take operators which, let's say, initially commute or anti-commute, and then use the commutator or anti-commutator square to define this object for any body system, and try to see what happens. And what you specifically look at in many situations is rather than looking into this commutator square expectation, you look into some part of it, which is this thing which is called the out of time order correlator, simply because the time ordering is not like the standard time ordering that we use in quantum many body physics. And one part of this will actually grow. I mean, this object itself will decay, and one part of this will grow, and that will again give you the Lyapunov exponent. Now, I'm going to talk about two questions related to this in this Lyapunov about this chaos, quantum chaos in many body systems. So one thing that I'm going to ask is how quantum mechanics actually affect chaos. What are the mechanisms? Now, there are known mechanism of quantum mechanics affecting chaos, and these are related to many body or in general interference effect, quantum interference effect, which has been talked about a lot in non-interacting systems. These are clearly understood, and even for some interacting systems close to their classical limits, this has been out. And the main thing is that there is a time scale which is called this unphased time, or also the scrambling time, beyond which you will actually have this interference effect, which is shown by some trajectories, classical trajectories interfering here, will actually kill chaos and saturate this OTOCs, which are typically some bounded OTOCs or bounded operators. So this will saturate. But what we are interested here is this regime over here, which is where initially, before this quantum interference effects comes in, this thing actually grows exponentially. Okay, and this regime effectively, this the extent of this regime where it grows exponentially depends on this quantum parameter, which could be h bar, or in some cases it could be in the large n theories it could be 1 over n, some parameters which is small. Okay, and what I am going to talk about is not this quantum interference effect. I am going to focus on this regime where actually there is a growth, and I am going to ask that in this regime, are there, so what kind of effects quantum fluctuations have? For example, if you change h bar or something equivalent to h bar, how this Lyapunov exponent actually changes over this window of scrambling time or the unphased time. So this is the first question. The second question that I'm going to ask is that how symmetry breaking phase transition, and let's say you have some critical dynamics or some slow dynamics associated with certain kind of phase transitions, how they actually affect this chaos. Okay, and some of this has been discussed for a long time, and recently also several people, including us, have looked into this in like paradigmatic transitions like Kosterlitz-Thouless transition or Ising transitions. And if you just study classical dynamics in some models which has some intrinsic dynamics like XXZ model, and you try to see what happens of this quantity across phase transitions, which has some, let's say, diverging time scales and length scales of different ways. Okay. And what you find that typically phase transition do not have much effect on these quantities, which probably understandable because these are sort of intermediate time or short time properties, this Lyapunov exponent is. And so generally what happens, at best you see some crossovers, not much effect of critical slowing down as shown by the system size dependence of this kind of systems. Okay, so we want to probe this further in quantum system because that was a classical system. Now one bit of motivation that why we care about Lyapunov exponents, especially in quantum systems. There are many ideas that have come up recently, but one thing I'll just mention is that the fact that the quantum mechanics has some fundamental role in this Lyapunov exponent, because it actually puts a bound on this object that for any quantum system it cannot be more than this 2 pi kBt by h bar, determined by the temperature of the system and the h bar. Okay, so this is this Maldacena bound, and this bound is interesting because of this long search of this Planckian understanding of Planckian dissipations, which are of course experimental fact that you see in many materials, many different kinds of material, at least things like transport scattering time. The transport scattering rate actually seems to follow some sort of universal trend, which is very close to this kind of behavior. However, this is not exactly Lyapunov exponent. So you would like to understand such bounds exist, or at least some relations between this transport scattering rate and Lyapunov exponent. Now, one systems where this can be calculated quite easily, as we understand now, is this Sachdev-Kitaev model. And this model, of course, is kind of a toy model. It's a zero-dimensional model, effectively some infinite range interacting models of interacting fermions, where fermions interact with some 4 fermion interactions in a random with random coupling, and they are like n sites and they are infinite range. And so this is kind of a large n model where n is this large n limit is the thermodynamic limit. And in this model, you can exactly calculate this Lyapunov exponent. So now, and it turns out to be exactly same as this bound. So now the question that comes, I mean, of course, these things are understood in SYK model. So one thing, as I said, that how quantum mechanics actually plays part, I mean, in this regime where you have a non-zero Lyapunov exponent. So the idea here is that originally chaos was a classical concept, and now you are looking into this Lyapunov exponent, which has a bound and which has some dependence on this h bar. Now, if you take this h bar dependence, then trivially it would seem that there, of course, cannot be a bound in the classical system, because when h bar goes to 0, this thing diverges. But what we are more interested, I mean, that is of course true, but then of course classical system have some Lyapunov exponent. Now imagine that you have a quantum systems where you can vary this h bar, and what you are interested in understanding that, is it true that always classical system will have larger Lyapunov exponent, meaning following roughly this trend of the bound? or it can be that somehow quantum mechanics some cases enhances chaos. So this is an interesting question, because chaos originally is a classical concept, and whether quantum mechanics can enhance actually chaos. For example, could there be different situations where it monotonically decreases with h bar, or actually it has some non-monotonic behavior? Okay, so this is the kind of questions that I'm interested in when I say that I vary this h bar, this quantum limit. But in this case, this SYK model won't work, because this is a fermionic model. I mean, you cannot take classical limit. And secondly, the symmetry breaking, I mean, there are some models with symmetry breaking in SYK type things. But I mean, typically the dynamics is not that non-trivial. And I'll try to explain what I mean by this non-trivial relaxation. So we want to go into some other model where both of these things can be done, meaning that you have some h bar which you can tune, and even after taking the large n limit. And then secondly, whether there is some symmetry breaking, and the model which naturally is sort of connected to this SYK model, where you can do it nicely. And the simplest kind of model, which is also very well studied, is this model that I'll discuss, which is this model of some kind of quantum solvable model of quantum spin glasses. And what I'm going to discuss is a phase diagram of the chaos, where I'll discuss the chaos as a function of h bar and temperature, and the different kinds of interplays of fluctuations, symmetry, and glassy dynamics which appears in this model. And another interesting thing about this particular model that I'll be discussing, which again, as I said, is related to more classical systems, which is that this model that I'll describe it's a well-known model, as I said. And in the classical limit of this model actually describes this what are known as this Mott coupling dynamics of supercooled liquid in structural glasses. I mean, it doesn't describe the dynamics of supercooled liquid all the way through the experimental glass transition, but it describes over a large regime above the glass transition. So this hence, by looking into this model and taking the classical limit, which is that h bar going to 0, will be able to actually capture the chaos in supercooled liquid. So that's another motivation. And we'll see that in this kind of glasses, there are this complex relaxation. I will not go into the detail of it, but the main thing is that as your temperature becomes sufficiently lower, close to the glass transition, then you try to start seeing complex relaxation, namely this kind of two-step relaxations with different regime of dynamics. And the particular regime I'll be talking about, which is described by this stressed exponential relaxation, where there is a time scale of this stressed exponential which diverges approaching this putative glass transition. And what we are going to ask that what happens to this lambda L inverse, how is it connected to this, and how the glassy relaxation can influence chaos. Okay, so this is the model, and as I said, it's a very well studied model in in quantum spin glasses. So basically you can think of this model is a particle moving on a n-dimensional hypersphere. So effectively these spins are nothing but positions on the surface of a sphere which is constrained on a surface by this spherical constraint. And you put quantum mechanics in this model by just putting a kinetic energy and the canonical commutation relations between this momenta and the position, okay, or the spin in this language. So this has some dynamics. This model has this multi-spin interaction, which is called the p-spin interactions. Again, there is some typo here, but basically these are random, typically taken from Gaussian distribution. So this is similar to SYK in that sense, that you have some multi-body interactions interacting with some random coupling. And what I'm going to discuss is this phase diagram, as I already mentioned, as a function of h bar and temperature. So in this model, we can actually tune h bar continuously. And the two main things that I'll be focusing on is this classical paramagnet, which is not too high values of quantum fluctuations or h bar, somewhere here above the glass transition, which is denoted by this line. And here the glassy phase is a replica symmetry broken spin glass phase of certain kind that will be discussed. Okay, so this is the thing that I'm going to discuss. And as I said, that if you take h tending to 0 limit, then this regime you actually describe the dynamics of supercooled liquid over certain range. Okay, so some technical things I'll go very quickly over this. So do the theory, what you have to do it basically look into this kind of spin glass overlaps. but now it is dynamical. So it's kind of a correlation functions, but overlap in principle between different replicas. And eventually you have to take this replica going to zero limit. So this model is solvable. So you can exactly find out the equations that governs the correlation functions and exact given by some exact self. The main thing is that naturally of this which appears in the kinetic energy term, and what we are going to do is going to tune h bar, keeping this mass fixed, because that gives a non-trivial classical dynamics. Okay, so now to describe the paramagnetic state is easy. So this quantity, this correlation function, which has different replica indices, become actually diagonal and symmetric. So one can easily describe that. Describing the spin glass state is slightly more complicated, but these are all well understood, because as I said, the model has been studied so much that everything almost understood about this model. And it turns out that the replica symmetry breaking offers the simplest kind that one can have, which is this one-step replica symmetry breaking. Again, I'll not go into the detail of this. If you are not familiar or interested, doesn't matter too much. Basically, you have some structure. These are matrices in these n cross n matrices. So you take some ansatz for the mean field or the saddle point theory, where you put some ansatz about the structure in the replica space, and eventually, of course, you have to take this n tending to 0. So in this structure, you get these blocks of size m, and what you can do is eventually what appears here is the important thing is the spin glass order parameter, which is this well-known Edward Anderson order parameter, which appears in this ansatz, and you find this all this self consistently, and we look into a certain kind of spin glass phase. Again, the details doesn't matter. Okay. So now one additional thing you have to do here compared to the things that have been done already in this thing, that we are looking into this out of time order correlator, because we want to characterize chaos. And this is slightly, at least when you start with it, it looks slightly non-trivial, because you have to look you look into certain out of time operators. I mean, I'm using some regularized operator for some technical reason, but again, that is not important. So important is that you have this kind of out of time ordering of the operator, this quantum operator, in this case the spins or the positions, and what you have to do is you have to formulate it in some real-time dynamics, and these are typically done using some Keldysh contours, in this case, which has these 4 branches, etc. And for paramagnetic phase, it is pretty straightforward. It's just generalization to these 4 branches rather than standard 2 branches in the Keldysh. But however, it turns out that if you want to describe the dynamics in the spin glass phase, then you have to actually include the replicas even in the Keldysh formalism. Okay. So this is slightly non-trivial part, and once you do that, you have to now understand what is the replica structure of this out of time order correlator, and eventually you have to take n tending to 0 limit. But although all of this can be done, and once you do that, basically you can extract this Lyapunov exponent from this object, and that's what we did basically. So again, some details here. So the main point is that what you obtain here to obtain the part which grows like this e to the power lambda LT, you basically for that part you can write down some kind of ladder Bethe-Salpeter equations, which looks like some integral equations which you can solve, and the input to the integral equation are the solutions from the saddle point. For the solutions for this correlation, this overlap correlations that I mentioned earlier. And one important part here is that how does this spin glass information enters, and that enters, it turns out, through this thing which is called the Whitman correlator, which connects the rung, which is basically rung of this ladder. And it turns out the way the spin glass is different from a paramagnet is by the addition of the, so in this quantity, basically this Edward Anderson order parameter enters, and that's how that's what distinguishes the spin glass and this thing. And again, you can solve this and try to find the Lyapunov exponent within some ansatz, and that's what we do. So now let me discuss the results. Okay. So first, let's do the simplest thing, which is the spin glass, the paramagnetic phase. And remember, what we are asking is that what happens as a function of h bar, and also let's say as a function of temperature. And I'm somewhere here in above the glass transition, which is this red line. Okay. So first, what you see that if you are sufficiently high temperature from the glass transition, then the approach to the classical limit is basically monotonic. So as a function of h bar, and you approach the classical limit, and in this class, indeed the classical system has larger Lyapunov exponent, so they're more chaotic. But what you find that as you approach the glass transition, then this actually changes, and you start getting actually non-trivial quantum mechanical effect where these things become non-monotonic as a function of h bar. So you can have some regime of quantum systems which has a larger which is more chaotic than the classical counterpart, and similar things is also seen as a function of yes.
Sorry to interrupt. You have about 3 minutes and then 5 minutes of question and answer.
Okay. Yeah. Thanks. Yeah. Thank you. Okay. So you basically see the same kind of thing as a function of temperature, that there is some kind of a broad maxima in lambda L. I mean, some non-monotonic dependence essentially. So now, so going to the spin glass phase, so what you find that so again the same question, that what happens, what does quantum fluctuation do to the chaos in the spin glass phase, which is a replica symmetry broken phase here. And what you find that here actually the opposite thing happens, that in the symmetry broken phase, h bar actually almost always increases Lyapunov exponent. So it makes the system more chaotic when you add quantum fluctuations. And I mean, you can obtain some power law dependence of Lyapunov exponent, etc. Okay, so that I'll just keep in the interest of time. So now what you can do actually, you can find out in the spin glass phase also analytically this Lyapunov exponent. So it turns out that you can solve these equations analytically, these equations that I mentioned, which gives you the Lyapunov exponent. You can actually analytically solve by mapping into a very well-known quantum mechanical problem. And this is very similar to actually what I mean. So this spin glass phase actually very similar to this kind of Fermi liquid thing that people have looked into. And you can so the main reason, so okay, so the main reason, so first of all you find some temperature dependence like T square and all, but so the main thing that I'll focus on here is that why the Lyapunov exponent increases as a function of quantum fluctuations, and the reason turns out to be quite simple. So the reason is that the Lyapunov exponent turns out to be sort of have an inverse relation with the order parameter. And as you increase h bar, it certainly reduces the order parameter. I mean, it tries to destroy the order by increasing quantum fluctuations tuned by h bar. And as a result, Lyapunov exponent actually increases as a function of h bar in the spin glass phase. So now the last bit, which is this, as I said, that what is the relation between the relaxation and chaos. So chaos gives you one time scale, the relaxation, which is, for example, obtained from spin-spin correlation, gives you some other time scale. And as I said, that there is some complex relaxation in this system, so which we can see also in our calculation. So you start, as you go to lower temperature, you start seeing these two-step relaxations. And you can extract the time scale of this long relaxation time. As you can see, it's a very long relaxation here. And this time scale, as expected, it diverges at approaching the glass transition. However, the Lyapunov exponent, or the Lyapunov time, the inverse of the Lyapunov exponent, that doesn't diverge. I mean, that is finite here. But more importantly, as I showed earlier, that the Lyapunov exponent has a maxima, which means that this quantity has a minima. So there is some kind of scale here, which is emerging. So the question is, what determines this scale which is above the glass transition temperature, and how relaxation, if at all, has any effect on this. And so this minima where actually this two-step relaxation first onsets, meaning in the glassy regime you see this complex relaxation at the temperature where this onsets basically seems to be same as where you get the maxima in Lyapunov exponent or minima in the lambda L inverse. So in some sense, the relaxation has some correlation with this, and we can actually not exactly this correlation, but we can actually understand. Then I'll just not go through the details. So basically, we can show that again. So you can solve these equations analytically in this regime of glassy relaxation. So namely you have, we do some approximation. Glassy relaxation is actually stressed exponential, but to solve it you actually take some exponential relaxation like the standard Debye relaxation, which is ubiquitous in liquids and all. But the main thing is that you have some relaxation time which diverges approaching the glass transition, and you can actually find out a relation, not exactly at the glass transition but slightly above it, as with the relaxation time. And what you find that indeed initially the relaxation time is or inverse of the relaxation time is proportional to the Lyapunov exponent. So in some sense relaxation do control the Lyapunov exponent, but there is an additional bit, which is that there is some kind of crossover from strong to weak coupling, where this J, when J become comparable to temperature, then again it starts getting reduced, and as a result you get this broad maxima. So we can get similar kind of thing in the Sanyal model, but I'll just skip it and just main summary. So I showed this quantum fluctuation, how it affects this chaos and all. So the one thing I think interesting is that in some sense it gives a new way of looking into dynamics of supercooled liquid through chaos, and it seems to have some relations with relaxation, but not exactly same. Okay, so with that I'll thank you for your attention, and sorry for taking a bit longer, too much longer.
Yeah. Thanks, Sumilan, for your nice talk. So there's time for maybe one question or two. Yeah, Debanjan, please go ahead.
Hi, Sumilan, that was a great talk. Thank you. I was wondering if you could speculate on the following two related things. So if you go beyond zero-dimensional models and bring in some spatial structure and locality, in the presence of a few conservation laws, can you comment on how the growth of chaos might be affected?
Yeah, actually, so you mean with just the fact that you include locality, or also?
Right. I was just wondering, like, when you, near this last position, if you have spatial structure, does chaos still grow ballistically? And if you also have some conservation laws, how does that connect to the, the diffusively growing?
Okay, that's a very good question. Actually, this is something I don't know the answer. So we have been actually studying this using Sanyal model. So what we do is this kind of lattice of Sanyal model, exactly kind of thing you probably have in mind, and you try to see as you go to the glass transition. So how, so as you go to the glass transition, there is some change of transport, right, from the above the glass transition. So we don't exactly know what happens to the transport of this type of model of this, let's say the quantum dot of Sanyal put on a lattice in the glassy regime. So we have not actually yet studied about it, but this is something we have been trying to understand, that how, if you have some anomalous dynamics, anomalous diffusion or something in this model, so how it would affect this chaos. But we actually have not, I don't have any results for that. We have just started to studying, actually studying this question that you are asking.
Thank you.
Yeah, it's a good question. Thanks.
All right. Thanks, Sumilan. So maybe you can unshare the screen now. And is Sambudhha around?
Yeah.
Hi, Sambudhha. Yeah, so maybe you can try to share the screen now. Yeah. So Sambudhha, I'll give you a warning at 22 minutes so that you have 3 minutes after that, and then 5 minutes of question answer. Okay.
Okay. So when I go to this sharing, it shows some advanced sharing option. Who can share? Only host, something of this sort.
Oh, but I think you are a co-host.
Click on share screen and share your screen.
Yeah, now I get that. Yeah. Can you see it?
Yeah, so maybe full screen mode.
Yeah.
Yeah. Okay, so the next talk is by Sambudhha from IISER Tirupati, and he'll discuss about emergent scale and critical dynamics in certain quasi-periodic systems. So Sambudhha, over to you.
Thanks. So I will like to start by thanking the organizers for two reasons. One is for continuing to organize this nice series of meeting, and for inviting me and giving me this nice opportunity to present here. So this talk is about some of the recent results from my group, which is on emergent scale and critical dynamics in certain quasi-periodic system. And this work is mainly carried out by a brilliant undergraduate who is in 4th year, Parvati, and a brilliant postdoc, Dintuman, who did all the heavy work and the calculations. And we have funding from the internal funding from IISER and SERV. So I will like to start. Why can't I change? Okay. I will like to start by a brief overview of the recent interest of the community and the overall interest in the quasi-periodic systems in general. So in condensed matter, normally we are interested about things which are fully periodic structures or completely dirty or like aperiodic. And there is a parallel development that happened almost since 80s that which is associated with quasi-periodic systems. So these are systems which are almost periodic. So they don't, it's not like that they never is a particular value of a potential or a hopping or some parameter, it never reappear, but it reappears in a very close manner and with a particular frequency. So that's what is the rough crude physics definition of quasi-periodic. And these systems are extensively studied in physics and mathematics in general. And it turned out most of the properties of these are deeply buried under like some kind of mathematical structures of these systems. And one of the first result was this localization transition in 1980 of Aubrey and Andre. And although this was before, even before that, Harper and all studied these kind of systems in the context of quantum Hall effect and magnetic effects on single particle metals. And then a lot of interest grew in over the last few years where these systems were experimentally realized and turned out to be a place to learn about all these different range of phenomena from starting from topological phases and twisted systems and then thermalization and MBL and etc. and even non-Hermitian physics. So in this talk, I will like to focus on some particular aspects and a particular class of models. About there are of course lot of additional things have been tried on this model since the starting point of the plain vanilla model of quasi-periodic system. And in this talk, I will particularly focus on a very simple class of model, which has a single quasi-periodic frequency. So this is what I'm defining the meaning of the certain quasi-periodic system. So what do I mean here? I mean, we will be interested about systems which has a single quasi-periodic frequency in the sense that a single number to characterize a single irrational number. We are interested about systems which are only one-dimensional, has local hopping, like maximum nearest neighbor, and most importantly, systems which has two parameters or two scales. So this is the main agenda here, is to study the effect of these two scales. And although it is tempting to see that what I'm going to say is perhaps a competition between these two scales, but I will see actually it is not, it's more like an emergent phenomena. So one of the main thing happens when you introduce two scales in this kind of quasi-periodic lattice model is appearance of a mobility edge that have been studied extensively in last 20 years. And even very recently, it was shown that it can happen that by changing a single parameter, the mobility edge can reappear, disappear, or reappear. So it's dubbed as a reentrant transition. So in this talk, our focus will be to understand what is the general criteria for this kind of phenomena, and to understand if a mobility edge is because of competition between two scales, or because of two parameter scales, if I avoid the word competition, then what are the statics and dynamics property, or what is the nature of criticality? Is it any different or anything new? So this is the scope of this work. So I'll start by a little overview of the plain vanilla model of quasi-periodic system, which shows a localization transition. So it's a model where you have a simple hopping on a 1D chain plus a quasi-periodic potential. And when you tune it from a low value to high value, the system goes from a delocalized to a localized phase with a critical point at lambda c equal to 2. And the main property of this transition is that the entire system, that all the states go through this transition. And it's irrelevant what irrational number you choose, unless it is super tiny, that's a separate question, but generally any irrational number shows that. And the critical states have some non-trivial dynamical signature, which means it looks diffusive if you look at the closed system wave packet spread. But if you look very closely, it has some signatures of non-diffusive, like sub-diffusive or some other things. So generally, it is initially motivated as like it's a template to study localization transition in 1D, because normally with disorder you don't get that, potential disorder you don't get that unless you are in 3D. But it turns out it is much more than that, because it's fundamentally different from how localization happens in true disordered model versus this. It's not interference phenomena, it's a property of the solution. And that's why it's very interesting to mathematicians also. So here I have shown some pictures of how the potential looks like. And some of another major reason of interest for this subsystem is that these can be nicely, these Hamiltonians can be engineered in a optical lattice system that have been done in 2015 by Emmanuel Bloch's group. And one can study this localization phenomena, although that was an interacting model, and the goal was there to study MBL. And one can study by looking at the dynamics of certain quantity, like one loads half of the lattice in alternate sides and see how does it spread out over the full system. And this quantity is called imbalance. And that can be studied experimentally to see this localization phenomenon. Now here we will be mainly concerned about system which has an additional scale. That additional scale can be introduced in multiple different ways. So, and there are actually many different ways, but these are the 4 different ways which are generally studied in and within the scope of local and one-dimensional interaction models. And the first one is a very well studied one in context of MBL is this model where you have a additional modulation in the potential. So if you plot the potential against the lattice, you will see that the black line is for the regular plain vanilla Aubrey model, and the red line is for this new other model. You see it introduces an additional degree of fluctuation. It's basically an additional tuning where you add the difference between neighboring sites and it adds an additional fluctuation. The other one was studied even before, like long ago. It is the spatial modulation in frequency, where you it is more, I think, a theoretical model where you introduce some power in the coordinate, and then you see that basically what happens that the potential modulates with an additional frequency scale which changes with the lattice coordinates. And then there are, in this talk actually we will also consider them, but we'll study 2 other category of 2-parameter models. One is where you introduce the second parameter in the off diagonal elements. It's like SSH type of chain, and there is no you cannot draw it as some nice modulation of the potential only, but it's entirely on the diagonal. And these are very interesting. In last 2-3 years there are several experiments etc. happened, and because of the reason of mainly from the perspective of topological properties, but not from exactly the localization and all that. And then there is another category you can introduce, which is not entirely different from these, because there can be some overlap between this 4th category and the other 3, is that where you view this problem as 2 periodic scales, which means you introduce an additional modulation, or you can think it is like 2 optical lattice of 2 different properties and they are superimposed on that. So we will see that what is the main difference and what are the general criteria appears in these 4 different class of systems. So for that, I will use the most standard canonical static probe to understand localization physics is the IPR. So IPR is nothing but the sum of the 4th power of the wave function at each spatial location, and it scales as a power law in general. And for a purely localized state, it doesn't scale. For a delocalized state, it scales as 1/L, and anything in between, it's a sign of criticality. A complementary quantity that was introduced in 2017 by the Das Sharma paper, where one can study an inverse of this IPR. So one might think naively these are just inverse to each other, and that is true for an individual state. But if you first take the average and then multiply them, then it turns out it detects a mobility edge, which means as if there is a mobility edge, it will be non-zero. If there is none, then one or the other quantity of IPR and NPR is 0, and you will get a 0. So here is a demonstration of that for a certain model, that it is non-zero only in a regime when it has a mobility. So it's just a mobility as detector and nothing more, but it's a very useful detector. So this, if you apply this for one of the standard models with 2 parameters, it was shown earlier that this model has a mobility edge. The dark regime implies a localized state, and the bright regime implies it. Sorry, dark regime is delocalized state, and the light color is localized state, and there is a transition between them in a single value of parameter. Now it turns out in very recent experiments. So this one particular experiment on this slightly peculiar looking model, but the main idea of this model, it's a potential when you tune this parameter beta, you go in one limit, you go to the Moiré on the model, other limit you go to a Fibonacci sequence. These are like 2 particular kind of models. Quasi-periodic model, one has a localization transition, other doesn't, other has all the critical states. And it was shown that when you tune this parameter, the character of the mobility edge changes, which means what 2 different kind of state it separates. And this is an experiment on the right side, where that have been also verified. So this particular plot in the top for the smallest energy state, but if we do a state average IPR, we will also see that there is a transition in the even in the average states. So this is one of the reason that one interest that we hint that a second parameter, how you introduce a second parameter, can lead to new and interesting range of phenomena. And then there is another set of paper from over last 2 years from this mainly from Tapan Mishra group and this Gong Lu Cheng, and they indicate that if you have a 2 parameter model which is of this kind, of the kind where the second parameter appears in the off diagonal form, which is a SSH kind of model, and if you plot this quantity eta, which basically detects a mobility edge, you can see a re-entrant phase transition, which means if you tune a single parameter, you will see the system goes through first a localization, goes to a state with mobility edge, then the mobility edge disappears, and then it reappears again. So that's a very interesting phenomena. And then it was shown that it was mainly studied for these variants of Rice-Meilley model and SSH model, where you have take the Rice-Meilley and SSH model and introduced add a quasi-periodic potential to it. And another model was also studied where you which is of the category where you add a additional dimerized potential of plus and minus value. So these models are actually also realized for other purposes in experiments, like for topological phases and all, but not for exactly this kind of studies. So these are pretty close to real world systems also. So here is the other result on that. So when you tune a single parameter, you go from a series of, this is from another paper from Tapan Mishra's group, that you will go from a series of transition where the system has a mobility edge, then the mobility edge disappears and it reappears and so on. So based on all these recent developments, we asked these 3 questions. First, we want to understand what is the general criteria for a transition of existence, or on a transition on the existence of mobility edge, and what is the nature of states that appears at the critical point of such a transition, as we understood earlier the subtle properties of the simple Moiré on the critical states. And there is what is the signature of those critical states in dynamics and transport, especially in the experimental region. So I'll first give the answers to this question, and in the rest of the talk, I will give you the evidence for backing up that answer. So what we found is that this transition in the existence of mobility edges by tuning a single parameter can happen in any model that has 2 periodic scales. And this is an emergent phenomena in the sense that you cannot, if you view this model as a, like if you switch off one of the scales and you see this one model and switch off the other one, it's another model, but it's a property of none of the parent models. So it's in the, you cannot connect it at least as far as we have tried. And our evidence is mostly phenomenological because we basically studied all the models in this category. We cannot yet prove that that this must happen. And the second conclusion is the frequency of this quasi-periodic frequency, in a quote-unquote frequency, because it's not a periodic object, and it sets the energy scale, that at which scale the mobility edge will appear, and it also sets the number of transitions. This is again something not generally in the general Aubrey-Andre phenomena, you know that it's a choice of irrational number doesn't alter the pair. But here it not only sets the whether you will get at a mobility edge or not, it will also sets at what energy you will get that. So, and then the other conclusion we have, the third conclusion is even more interesting. We found that there is a very rich phenomenology, a rich range of behavior in the dynamics. You will find states like subdiffusive, superdiffusive, and diffusive behavior, and even the character of the dynamics we can change with time, and that's mainly because there is always a cocktail of different kind of critical states which affects the dynamics in different ways. And finally, we'll give a proposal in one of the well-studied experimental setup, and where the setup is already studied extensively, and the quantities that are possible to measure, and we will propose an experiment or propose an outcome when one measures those things for these models. So let's start with the evidence for the first conclusion. So we studied all these models that are available, and some variants of that, and well, if not all, but most of them. And I show evidence for 4 models. The left 2 are the SSH and on-site staggered potential, which have been shown in the literature already. And the right one is Rice-Mealy, which is also there. And the bottom one is the bichromatic model, which is basically taking 2, and that is actually closer to experiment. Normally, you think you create a potential and a quasi-periodic potential, and that is the theoretical model. But in experiment, what you do, you have one optical wave, and on top of that, you impose another optical wave. So it's effectively a bichromatic model. The character is by a single frequency, and the second one is double to that frequency. Even that has this kind of reentrant transition. And the transition where the mobility disappear and reappear when you tune a single parameter. And it doesn't happen in the models which you cannot think as 2 periodic scale. So the most canonical model is this Das-Herman and Pixley model. And then the other model where you have a slowly varying potential. If you change the potential, like change the frequency, then you can see the reenter. But if you change the energy scales of the problem, then there is no such transition. So then the second conclusion is that this quasi-periodic frequency sets the energy scale of the mobility edge and determine the number of transition. So in the left plot, you can see we have shown that this reentrant phenomena for the SSH model, and you can see the parameter scale. The delta needs to be like as large as 40 and lambda needs to be as large as 15, and this is for the golden ratio. But if you do the same for some other, so notice that only the fractional part of the irrational number matters, because the integer part is, of course, the periodic part will drop out, and there is a symmetry between that number, the fractional part, and 1 minus that fractional part. So if you tune it to something else, some golden ratio plus bold ratio, we can go very close to 1 or very close to 0. And when you do that, you can see the same plot, the same phenomena is appearing in a range of 0 to 4 in x and y axis of delta and lambda. So you set the scale at which this transition will happen just by tuning the frequency of the optical lattices. And then we have shown also for a defined ratio that how many such transitions happen, that also is the same model, all of them same model, how many such transitions happen determined by that frequency. So now a more closer to experiment model, which is this bichromatic model, that is been studied already in experiments and also extensively in theory, and where if you have this two optical lattices of same, they have the same quasi-periodic number, but one is double to other, then you see a multiple transition, and you can of course tune the number of such transition by tuning the alpha. That is what is our conclusion. So now I will give a quick overview on the critical property. The third conclusion, we said that the states that appear in the mobility edge are this mobility edge are critical, and of course that is not very surprising, and the criticality is very different from the one we know in other quasi-periodic models. So first of all, you cannot use the standard analysis of IPR versus average IPR scaling, because it's a mixture of states, and most states are either localized or delocalized. But if you do a state resolved IPR, which means you plot the IPR for each state and scale them, then you will find they are collapsing on top of each other, which if you look at the left plots, they are you can show that they are localized, most states, but some states are not localized. And when you multiply it by n, then you expect the delocalized states to collapse. And then you can also show that the states are neither localized nor delocalized. But you cannot, it's not so easy, at least so far, what we have tried, that to pin down the exact critical nature, because there is not only one type of state, there are multiple type of critical states. So one can perhaps look at state by state, which is a very tedious task to know the exact nature of these critical states. But if you look at the dynamics, something interesting happens, then this nature of the critical states become much more clear. So we know that the simple Abreande model already shows some peculiar behavior in the critical states, although and that is one of the reasons it's very different from the localization transition in 3D. So it has this the center and edge of wave packet turns out to move differently and have some subdiffusive signature in two-terminal transport. So we looked up at on the dynamics in this model. So the scheme is very simple. You take an initially localized wave packet and see how does it spread. And if it is diffusive, if it will spread as linear in T, the wave packet width will grow as linear in T. Ballistic will be T square, and the localized will be exponentially suppressed, or anything critical will be something in between ballistic or diffusive, or diffusive and localized, either super or sub-diffusive. So if we plot a dynamical phase diagram, but the color code is the power alpha, and we see that there is a transition, and the transition points are marked by this blue dot and black dot, and they show truly super diffusive and sub-diffusive behavior, as I have shown in that other plot at the bottom. And we have extrapolated this thermodynamic limit behavior, and this is indeed a super diffusive or sub-diffusive behavior in the cases where we mark it. Then we also notice another further range of phenomena, that this diffusive character can change with time also. Like there is, if you plot the M towards ST, there are two slopes, and you can look it also in the light cone to show that when it's getting flat, it's flitting flat because of hitting the boundary. But that is not always true. We found there are systems which is a bit peculiar, because normally if you have a spectra which has some localized states and some delocalized state, in long time always the delocalized state will take over and control the dynamics. But it turns out there are cases where at long time the system gets localized. So if you look at the light cone diagram, you'll see the wave packet is not spreading anymore, and it is not, it is, yeah.
You have 3 minutes left, followed by 5 minutes of Q&A.
Yeah, I'm in time. Yeah. Okay, so you will see that it is neither localized, it is not hitting the boundary, but it is getting localized. And this point we don't really understand, that how come the system can have a critical behavior at short range, but at long time it is taking over by localized behavior. But probably I think this can be understood by the clustering of the wave of the eigenvalues, but that is something that needs to be checked carefully. So then we finally come to another dynamical probe, which is something was done in an experiment in Emmanuel Bloch's group. The idea is very simple. It's like if you have a box of gas and you confine all the gas particles in the left half, and then you suddenly remove a partition which confines all the particles on the left half, the gas will spread in the right half. And how much it spreads as a function of time, that will tell you how localized or how delocalized it is, and that can be experimentally measured in these optical lattice systems. And it turns out that if it is, for example, if you look at the bottom left plot, you will see that it grows with time. So that's a sign of not localized, being localized, can be critical or ballistic. Or if you see the middle plot, you will see bottom plot, you will see that the numbers are very tiny and it is fluctuating. So it's a sign of that the gas is not spreading at all. So if we do this and we plot this spread in the right half and against time, and after a long time, and you map it on a color code, you will find the sign of this transition in mobility age and re-entry behavior, the signature of this in a very much experimentally measurable setup. And we particularly point out that this bichromatic model, which have been already realized in experiment, and this particular measurement being already done, that if you do this and you will clearly see the signature of this transition, and even if you tune this optical lattice frequency, you can clearly see this emergent scale phenomenon. So that's where I will end, and here are the key takeaway points. So first of all, we don't know unless we go to this internal mathematical properties, that what are the exact mechanism of the critical dynamics. Well, it's not always a question of mechanism. In this case, it's sometimes just a property of the solution. And we found a transition in the existence, a general criteria of the transition. The transition in existence of mobility edge, and it happens in any periodic model, two periodic scale models. We found that there is a handle on the scale of transition using the frequency, and we proposed the possibility of studying this in a wide range of models and showed a rich range of dynamical behavior. And we think all these findings will have a interesting turn in the study of transport and MBA. Yeah, so that is all. So thank you for your attention. Now we can go for some questions.
Yeah. Thanks, Sambudhha, for your nice talk and also for sticking to time. So questions from the audience? Okay, maybe I can start off. So Sambudhha, you showed this thing where you started with the step function, right? Where all the particles were, yeah, exactly. So when this front propagates, right, for these quasi-periodic potentials, can you even characterize how this propagates, and is there
so
an
these are two
interesting
examples.
exponent there? Right, yeah.
Yeah, the exponent part I didn't look at, but it's very interesting to look at. But what we did is basically, we took the long time average value, and this the right bottom plot is basically that. And you can see the numbers are very tiny in a localized phase, and it can be a bit bigger. The middle plot at the bottom is a localized phase, and the plot at the left is for some delocalized phase. And you can see that number difference mainly tells you it is localized or not, or the transition at least. But the exponent point is a bit subtle, and I think it will be very interesting to look at. But we didn't yet.
Right. I see. Yeah, that might be
these
interesting.
have been studied in case of imbalance, so it's definitely an interesting question.
Yeah. Okay. Anybody has any questions? You can just unmute and ask.
Maybe I can ask a question.
Yeah, sure. Yeah.
Arnob, is it?
Yeah, of course. Go ahead.
So, Sambudhha, if you have the mobility edge, okay, and in these models, I mean, there are two things that usually come up, right? That one is that there's a mobility edge, and so there is some exponent related to how the localization length is changing around that edge. And then there is another thing, that these mobility edges are in your models would often pass through the band edges, which would also have a Vanov singularity. Okay. And so if you go back to your original models, they would have Vanov singularities. So do you see anything special when the mobility edge, hits the Vanov? Or no, you haven't?
No, I didn't think about that point at all, but it will be interesting to think that. But what I can tell that these mobility edges are not really a point here. It's a region. Oh, well, you can say, well, mobility edge is always a point, but the critical phase is a region, and this region cannot be characterized by a single exponent and all that. So if you try to find a scaling function, or different states are doing some different kind of scaling. So it's not easy to track down that. And the Vanov point, I didn't think about it carefully at all. So I have to,
because usually when the mobility edge hits the Vanov, your exponents change, and they are related to both how the localization length change and how the density of state diverges.
Yeah, so this whole exponent question is a bit difficult because of this reason, because you cannot, I mean, you have to look state by state, and that's a bit tedious. I have not yet figured out how to do that here.
Okay.
I see no other questions. So thanks, Sambudhha. So maybe you can unshare the presentation. And Indrajit, are you around? Maybe you can then share your presentation.
Yes.
Yeah. Okay, so right, it's visible. So Indrajit, maybe you can go full screen. Is it possible for you? Full screen mode?
Yes.
Yeah.
Yes.
And since it's a short talk, I'll give you a warning at 11 minutes and you should conclude 2 minutes after that. Okay.
Okay.
Yeah. Okay. Please go ahead. Yeah. So 1 second. Sorry. So the next talk is by Indrajit Sau from IACS, and he'll talk about the universality class of thermodynamic phase transition in Z2 quantum linked model. So please.
So thank you, Arnob, and I want to thank organizers for giving me this opportunity. So I will be talking about universality class of thermodynamic phase transition in Z2 quantum link model. This is ongoing work in collaboration with Arnob from IACS and Banerjee from SINP. So I will roughly follow this outline. First, I will talk about U1 and Z2 quantum link model. Then, in brief, I will discuss the quantum Monte Carlo cluster algorithm method. Then I will show few results, and finally summary and outlooks. So, quantum link model is a generalization of the standard lattice gauge theory. In lattice gauge theory, we define a parallel transporter on the link connecting two adjacent lattice sets ux mu, and we define a gauge invariant placket variables u placket like this. In quantum link model, these classical link variables are turned into quantum link operators. So small ux mu turns into capital ux mu, which is a quantum operator, and small u placket variables turns into capital U placket operator. And in the simplest case, there are two possible flux states per link, plus half and minus half, which have been shown by these arrows. And these placket operators, U placket and its conjugate, they basically flip a flippable placket and annihilates a non-flippable placket. Now we can construct a Hamiltonian using this placket operator, U placket and U placket dagger. So the first term of this Hamiltonian, it basically flip a flippable packet, and second term, which is called the Roxer-Kivensen term, this basically gives the number of flippable packet in the configuration. Now for the gauge invariant states, we have to satisfy the Gauss law. Gxi equals to 0 for charge 0, that is at each lattice set x, in and out fluxes add up to 0. There are total 6 possible charge 0 configurations, which have been shown in the first row. And we can also place static charges by locally changing the Gauss law, like Gxi equals to Qxi, where the Qx is the charge at the site x, and Qx can have the values plus minus 2 and plus minus 1. This is a plus 2 charge configuration, and this is minus 2 charge configuration. And these are 4 possible plus 1 charge configuration, and these are 4 possible minus 1 charge configuration. Now the general gauge transformation operator can be written as V equals to product over all the gauge transformation at each lattice site x, where alpha x is the gauge parameter and gx is the generator of the transformation. And for the gauge invariant Hamiltonian, we have V dagger is equals to h, and for gauge invariant states, we have to satisfy V psi equals to psi. Now, if we allow 0 charges only, then gx equals to gxi equals to 0 for all lattice sites x. So it can be shown that for any value of alpha x between 0 and 2 pi, this relation V psi equals to psi is satisfied. So this is a U1 theory. Now, if we allow charges plus minus 2 along charge 0, then there are 3 possibilities. Gx equals to 0 for charge 0, and Gx equals to plus 2 psi for charge plus 2, and minus 2 psi for charge minus 2. Then one can show that the only possible values of alpha x are 0 and pi, for which this relation v psi equals to psi is satisfied. So the theory effectively becomes Z2 theory. This is a typical U1 configuration on a 4x4 lattice, and this is a typical Z2 configuration on a 4x4 lattice, where there are plus minus 2 charges along with 0 charges. Now this is a specific heat and average of charge curve versus beta graph obtained using exact diagonalization method, and this graph showed some initial hints of thermodynamic phase transition. Now the cluster algorithm method. First, we have divided the lattice into two sublattices: the even or A sublattices, the shaded plackets, and the odd or B sublattices, the white plackets. Now, for the sake of the algorithm, now we have shifted to height variables from link variables. These height variables, they are situated at the dual lattice sides of the actual lattice, that is at the center of the plackets. So we basically shift from flux variables to the placket variables. And since the flux variables are restricted to two sides, two states per link, so the height variables restricted to two states per placket. So we assign 0, 1 for the even dual sides A and plus or minus up for the odd dual sides B. This is the pictorial representation between flux to height variables. The features of the height variables. So there are 2 to 1 mapping between these flux variables and height variables. So for a configuration in the flux variables, there are exactly 2 corresponding configuration in the height variables. Now these are the charge configuration in terms of the height variables. First 2 rows are the charge 0 configuration. There are 12 charge 0 configuration in language of the height variables, and and these 2 are the plus 2 configuration, and these 2 are the minus 2 configuration. And note that the plus minus charge configuration is not possible in terms of the height variables. Now this is the height patterns associated with flippable packets on the odd sublattice. Note that there are particular patterns associated with these flippable packets 1100 or 0011. So if we change the value of plus half to minus half, we basically flip a packet. And this is the general representation of placket on the time slices. So M1, M2, M3, and M4, they reside on the time slice T, and M5 reside on the time slice T minus 1, and M6 reside on the T plus 1 time slice. And we are only allowed to change plus up to minus up if the height configuration, the height variables on the time slice T, that is M1, M2, M3, M4, they basically forms the particular pattern. That here it is 1100, so we have changed the value plus up to minus up. Now from the results from quantum Monte Carlo, this is a benchmark between exact diagonalization and quantum Monte Carlo results. So the CV versus beta, these are CV versus beta graphs. So red curve shows the exact result, and the green points with error bars, they show the quantum Monte Carlo result. So the nice agreement between these two results prove the efficiency of the quantum Monte Carlo algorithm. Now we have calculated the two component order parameter MA, MB, where MA or MB are the magnetization of A or B sublattices, and we have defined a second order Binder equivalent corresponding to this order parameter like this, where M square equals to MA square plus MB square, and this is the second order Binder equivalent versus beta graph, and here is a crossing among these curves which have been shown in this inset panel. So, so there is a thermodynamic phase transition in this model, and this is susceptibility versus beta graphs for various system sites. Now we have used the finite size scaling method to calculate the critical quantities. So the Binder-Kumar crossing point beta cross between the system size L and alpha L, where alpha is some integer other than 1, follow this scaling laws. Beta cross L alpha L equals to beta C plus B L to the power minus U. So this is Binder crossing point versus 1 by L graph. The blue points are the actual crossing point, and the red curve is the fitted curve. So from the fit we can find beta C. Here we have got beta C equals to 0.14303 plus minus error bars. Now the susceptibility scaling. The
Indrajit,
yes,
you have about 2 minutes. Okay. And
okay.
yeah.
So the position of the peak of the susceptibility beta max corresponding to system size L scales like this: beta C minus A L to the power minus 1 by nu. So we can fit the data corresponding to beta max L and get the value of the critical exponent nu and beta C. Similarly, we can fit the maximum value of susceptibility corresponding to various system size L, and according to this scaling relation, and get the value of gamma by nu from the fit. Now the results from finite state scaling analysis. What we have done here, we have gradually discarded the smaller system size and obtained the values of nu and gamma by nu to see the finite size effect on the result. And here L mean equals to 32 means we have taken the system size 32 and the higher system size, and similarly L means equals to 64 means we have taken 64 system size 64 and the higher system size, and obtain the result. And here we can observe that the gamma by nu ratio is close to 2D Ising universality value, which is 7 by 4, and the values of nu decreases as L mean increases. So this shows a strong finite size effect. So we have to incorporate scaling correction to find the precise value of this critical exponent. Now the summary and outlooks. So we have formulated a 2 plus 1D Z2 quantum link model starting from 2 plus 1D U1 quantum link model. Then we have developed an efficient quantum Monte Carlo cluster algorithm method to study this model. And in this model, we have detected a thermodynamic phase transition, and we are in a position to find the universality class of this phase transition. And outlooks. So we have to incorporate scaling correction to find the precise values of critical exponents. Then we can study the behavior of the string tension in this model, and in future we will study the properties of the 2 plus 1D U1 phase transition. Thank you.
Okay. Thanks, Indrajit, for your nice talk. So we have time for maybe one question from the audience. So if anybody has any question, maybe the person can unmute.
Hello.
Or yeah.
I have a question actually.
Yeah, please go ahead.
How do you define the charges on the lattice like this? +1, -1, +2, -2 charges on the lattice. So we defined pictorially. So these charges, yes. So how do you define this +2, -2?
So in the simplest case, the flux variables are +½ and -½. Okay. So these are the flux variables. So for a zero charge configurations, so all the flux influx and the outflux, they add up to 0. So here this is total 0 charges here possible. Similarly, for +2 charges, you can see all the fluxes, they are outward. So if you sum over all the flux, then plus up, and plus up, 4 plus up fluxes add up to +2. Similarly here, for ingoing flux, they add up to -2.
Okay.
Similar for +1 and -1.
Good. Thanks.
Okay. Sumilan, quick question perhaps.
This dynamical scaling, I mean, this cluster algorithm, do you know how it changes? Meaning that this critical scaling down, how does it changes the critical going down?
So we have not studied the dynamical scaling in this model.
Study?
Sorry, Sumilan, can you be a bit louder?
Yeah, I don't know. So is it possible to study the dynamical scaling?
So actually, I don't know about this.
Yeah, the short answer is yes. The short answer is yes, and yeah, okay.
Okay.
Yeah.
So maybe I'll talk to you. Yeah.
Yeah. Okay. Okay. Thanks, Indrajit, for your talk. So maybe you can unshare your presentation.
Okay.
And Arnob, are you around for the next presentation? Yeah. Okay. Perfect. So yeah, we can also see your cursor. So good. So the next talk is going to be by Arnob Kumar Ghosh from IOP Bhubaneswar, and he'll talk about first and higher order dynamical modes in Floquet topological insulators. So Arnob, I'll give you a warning when 11 minutes are over, so that you have 2 minutes left to sort of wrap up your talk. Okay, so please go ahead.
Arnob, if you are speaking, we can't hear you.
Hello. Arnob, maybe you're on mute or something. Please
no, you're
check.
not on mute, but maybe it's not directed to the proper input.
Hello.
Yes, we can hear you very faintly right now.
Oh.
Maybe you can increase your mic volume in your computer.
Mic volume is full currently.
Okay. Just bring the thing closer to your.
Okay. Hello.
Yeah, better. Yeah. So Arnob, go ahead.
Okay. Okay. So myself, Arnob, I am a doctoral student at Institute of Physics, Bhubaneswar. So I have been working on the Floquet higher order phases, and today I will be going to present our recent work on this Floquet higher order phase. And my sincere acknowledgement to my collaborators, Professor Indrajit Sau, my supervisor, and Dr. Tanoy Nag, a postdoc at Aken University. So let me begin by giving you the definition of the higher order modes. So you know the 3D, the topological insulators, they are just like a bulk insulator, but the difference is that they show a gapless modes on their two-dimensional boundary. But in case of higher order modes, the two-dimensional surface modes are gapped just like the bulk, but the gapless modes appear at the one-dimensional hinges, or one can get the zero energy modes, separated zero energy modes at the corners of the system. And similar in 2D, one can also get the higher order modes at the corners of the system, and this is the second order topological phase. And for the more details about the higher order modes, one can look into these 3 papers. Okay. So today I will not talk about any static system. So I will be talking about the periodically driven system. So one of the feature of periodically driven system is to generate topological modes at finite energy. So before going to that, I would like to define some nomenclatures that I will be using. So in periodically driven system, one can get the modes, topological modes near energy 0, which we will call zero modes, and also modes near the energy omega by 2, which we can scale to pi, and I will call them as pi modes. So before going forward, let me give some previous works that has been done in this direction. So in this paper, the authors has introduced a model in 2D and 3D where they could host both 0 and pi mode, but they are only second order in 2D and third order in 3D topological modes are allowed. No hierarchy is allowed there. And also in the recent works, so one of our co-authors introduced a model where they find Floquet first, second, and third order topological phases in a hierarchical manner. But their study is kind of high frequency like, and they can get only the 0 modes, not the pi modes. Also, there has been experiments. So in these experiments, the authors propose a 4-step drive using an acoustic lattice, and using this experiment, they were able to actually show that they can get 0 and pi corner mode, and which are localized at the corners of the system. Okay, so with this previous work, so in this work, what we want to do is systematically generate the hierarchy of topological orders, and also in dimension. So in dimension means we will do in 2D as well as in 3D, and in 2D we can have the hierarchy like first order to second order, and 3D we can have hierarchy like first order, second order, and third order. And also we want to realize both 0 and pi mode. So let me introduce the Hamiltonian that we will be using during our driving scheme. So we use a 2-step drive. So in the first step, the H1 is basically one-side mass term, and in the second step, the H2 contains all the momentum dependent like hopping spin orbit and one alpha dependent mass term, and this alpha plays an important role in getting the higher order phase. So when alpha is 0, one get the first order phase, and when alpha is not equal to 0, one can get the second order phase. And similar in 3D also, we use the same 2-step drive, but here we have 2 parameters, alpha and beta. So when both alpha and beta are 0, we get the first order. When alpha is not 0 but beta is 0, we get the second order. And when both alpha and beta are 0, we get the third order. Now, without going to the analytical details, let me just present you the numerical results. So following our driving protocol, we can have this kind of phase diagram in J1, J2 parameter space, which can be divided into 4 parts. So in the region 1, one can get only the 0 modes. In region 2, there is no modes. Region 3, only pi modes, and region 4, one can get both 0 and pi modes. So I will focus only on region 4 here. So in region 4, to get the signature of the first order modes, we need to go into the ribbon geometry, and in ribbon geometry we diagonalize the Floquet operator and plot the energy spectrum, and you can see that there is a 0 mode close to the 0 energy, and there is also a pi mode close to the pi energy equal to em by pi. And if we plot the local density of states, you can see that the modes are populated near the edges of the system. Now we set alpha equal to not 0, as I have told. There I can get the second order mode, but here interestingly the phase diagram remains the same, and to get the second order modes, one needs to go to the open boundary condition in both the direction. And if we diagonalize the Floquet operator considering open boundary condition in both the direction, you can see that in the eigenvalue quasi energy spectra there is a 0 modes as well as a pi mode, and the modes are populated at around the corners of the system, and it is expected that the edges should be gapped. So if we plot the eigen spectra following the ribbon geometry, you can see that both 0 and pi edge modes are gapped. Now in 3D, the scenario is also the same. The phase diagram is almost the same, but only the here it is 3J2 instead of 2J2, and in the phase R4 we can get the 0 energy surface mode, surface modes crossing 0, and also a surface mode near pi, and the density of states is populated around the surface of the system. Now to get the second order, so we set alpha equal to not 0 and beta equal to 0, and in the phase 4 here also we can get the hinge mode. And to get the hinge mode, so here it is plotted in the rod geometry. So by rod geometry I means the system is open boundary condition in 2 direction, where of a periodic boundary condition in the z direction, and you can see the dispersive hinge modes in 0 and pi. And if we go to the real space system and plot the local density of states, you can see that the hinge modes are populated around the hinges of the system, and yeah, and this feature is qualitatively same for both 0 and pi modes. Also, now if we set both alpha and beta equal to non-zero, then one can get the third order phase, and in the region 4 here also you can see that we get both 0 mode and the pi mode, and they are populated at the corners of the system. Okay, now we have also considered another kind of drive. This is a mass kicking drive. So here we start with a Hamiltonian like J prime into H2, and instead of keeping it in a step, we kick it in a via a periodic manner. And here also we get a similar kind of phase diagram in the JM plane. But here the interesting thing is that as a function, here we can also get a phase transition as a function of time period or the frequency. As you can see, as we increase the time period, that is decrease the frequency. So at first there is no mode. Then you see that zero energy modes appear, and again after certain frequency or the time period, you can see that we get both 0 and the pi modes. Okay, so also in our driving protocol, by varying the certain parameters, we can get more number of Floquet modes at 0 and pi. So here in our nomenclature we have defined it as like n0 and pi. N0 means number of 0 modes per corner, and n pi means number of 0 modes per number of pi modes per corner. So here you can see here only 1 0 mode but no pi mode. Here 1 0 and 1 pi. This is like our region 4. I have shown this type of phase diagram in the previous slides. Now if we increase the value of J1 J2, you can see that here is increment of number of 0 mode, but here the pi mode remain the same. But in this region you can see that there is a double number of pi mode and 0 mode, and if we periodically increase J1 and J2, we can increase the number of modes more and more. So with that, I would like to summarize my result. So I have shown you the hierarchy in dimension, means we have generated Floquet modes in both 2 dimension and 3 dimension, and also we have hierarchy in the topological order. So in 2 dimension we have first order phase as well as the second order phase. In 3 dimension we have first order, second order as well as the third order phase, and we could generate both 0 and pi mode. Also in the mass kicking protocol we have shown you a frequency driven phase transition, and also there is a possibility of generating multiple Floquet modes. Also there is an issue currently that we cannot characterize this 0 and pi mode differently with proper invariant, because there exists some invariant but that rely on the mirror symmetry, but the model we are studying currently do not have the mirror symmetry, so we are working on that. Thank you.
Okay, thanks Arnob for your nice talk. So there's some time for questions, so if anyone in the audience has any questions, please go ahead. I don't see any questions, so let me start with one, Arnob. So if you go to your conclusion slide, so
yes,
you have these nice results about the edge modes and corner modes in your Floquet Hamiltonian, right? So, but it's sometimes hard to directly access the Floquet eigenvectors directly. So I was also wondering, are there any dynamical consequences of these modes that you may have studied? I mean, in these periodically driven problems?
No dynamical consequences we have studied. So here means in our driving protocol we can construct the Floquet operator exactly, so we can get the eigenstate exactly. in our directing protocol.
No,
But
yeah,
in-
I understand that, but because it's a Floquet problem, of course, it's hard to just go to some eigenvector directly, right? So typically, you just look at the dynamical properties in a Floquet problem. But yeah, but okay, maybe yeah, one can think about it. Yeah, yeah. Any questions or comments from anyone else? Okay, I don't see any. So thanks, Arnob, again. And I would like to thank all the speakers of this session for their very nice presentations. And let me pass over to Rajdeep if he has any announcements to make. Yeah.
Hi, everybody. Let's not only thank all the speakers, but also thank Arnob for chairing the session today. So thanks, Arnob. And no, the only announcement is that we meet again at 11:30. So the room for session 2 would be open at 11:20, and you can join in, and we'll see you there.